Hey, eighth graders, we are doing spiral review number 7. And we are starting off in the first section with something we've done a little bit more recently where we've looked at rational and irrational numbers. And I've told you guys what to look for. And I'll give you a hint when you want to look for an irrational number. It's like listening to some crazy little person on the phone going on and on forever and not making any sense, and there's no pattern to it, and it lasts forever, right? So an irrational number is going to go on forever, and it's not going to have any sort of repeating pattern where we could put a bar above it, okay? Everything else is going to be rational, okay? So most of the time you're used to working with rational numbers. Now, I'm not going to tell you that they're more irrational than rational, because that's a whole other conversation, but most of the numbers that we are used to working with are rational numbers. So if I look at a number like this, if I can simplify it so that it's a fraction or a decimal or a whole number, it doesn't matter if it's positive or negative, those things are all going to be rational. The things that you need to be on the lookout for are pi and non-perfect square roots. Now, non-perfect cube roots as well, but we really don't get into that much in the 8th grade. So look for pi or non-perfect square roots. So 16, the square root of 16, is that a non-perfect square or is it a perfect square? It is a perfect square. And if you're not sure, use the tools that you have at your fingertips. Okay, we know that 16 in our magical radical button tells us that the square root of 16 is 4. So you guys should be able to do that if you're not sure. At least you've got that tool in front of you. So this is essentially 1/4. 1/4 or 0.25 is a decimal. That is a rational number. So check that box right there. And then the square root of 19. Oh, I don't know if that's a perfect square. You should probably by now. But the square root of 19, press that magical radical button. And look, it goes on and on forever with no pattern like a crazy old person. So no offense to old people. Sorry about that. I will be old one day. In fact, I already kind of am. But that's besides the point. So this one goes on and on forever. Now the calculator has to stop. Okay, because calculator's got a job to do and it's done for right now, but it would go on literally forever if we kept doing that number. So that is irrational. There was a non-perfect square. Okay, I'm going to jump down to this one. Look, what's there? Pi. If I have something that's irrational, if I have 2 of those things, it's still irrational. Okay, something that maybe looks irrational, if I'm not sure, I'm going to take that and put that into my calculator, press the radical sign. Oh, it is a perfect square. Look at that. 17 is a rational number. Okay, so do the rest of those, rational and irrational, give them a check. And then make sure you answer the would you rather questions. Would you rather skydive or scuba dive? Me, scuba dive for sure. Actually, just scuba dived a couple months ago for the first time ever. And it was awesome. Actually, mostly awesome. I snorkeled one day and the next day I scubaed and it was awesome. But the second day, there was so much, there's a storm coming in and like I could see like the whole group of people like swaying with the waves under the water, and there's so much sand in the water because there's a strong current. So I would like to scuba dive, but not before a storm, and I did not like getting a little bit nauseous on that trip. So but I can tell you that's my answer. Okay, would you rather design clothes or cars? Would you rather live in a country home or a city apartment? Okay, I would have had a different answer for that depending on my time of life. Right now, probably a country home. But speaking of apartments, that's how I teach exponents. So how convenient for you all. These are some crazy looking apartments, and we've got some people in here some tenants. Those are people who live in a rental property. Tenants, they're going to want to move based on if their exponents are negative. Remember, we move them downstairs to make their exponent happy if it's negative, or we move it upstairs to make it happy if it's negative. So what you want to do first is move everybody to where they belong. So I'm going to redraw my apartment. Okay, and I'm going to move everybody to make them happy, and then I can simplify other ways. So I've got 12 hanging out right there. I also have a to the negative third. It's not happy, so we want to move it downstairs. So I'll just put that right there, a to the positive third now. So got that taken care of, got that taken care of. B is unhappy. Let's move B downstairs, and it will be B to the 4th. Check that off. 3's hanging out upstairs. It doesn't have an exponent, it's just staying right there. C is happy, staying up there. So those things are taken care of. Let's see how everybody's doing downstairs. 9's happy, 9 is staying down there. A is happy, A to the 2nd. Ooh, okay, we have 2 A's downstairs and 3 downstairs. Altogether, how many A's is that? Okay, think about what that means. We'll get back to that in a second. So we've done those two. B is unhappy. Let's move B upstairs and change that exponent to a +2. C is happy down there with a positive exponent of 8. All right, everybody got moved. Now let's combine and simplify. So there's no A's upstairs, okay? There's B's and C's, and then we've got these constants, 12 and 3. Well, we could go ahead and multiply 12 times 3. That's 36, okay? And then let's keep our letters in alphabetical order. So no A's, like I said, but we do have 2 B's. So I'm gonna put B squared, and then I just have 1 C. So it's kind of a cozy little upstairs apartment. Sounds like the party's downstairs. How many constants do I have? I've got a 9, so I can put that right there. I've got 5 A's all downstairs having a good time. Maybe that cookie lady is making fresh baked chocolate chip cookies, and everybody's like, so delicious, I want some. Can't talk about cookies or I'm gonna get hungry. We made a bunch of pancakes all day today in classes. So we learned about volume. Hopefully you'll be able to tell me all about it tomorrow as well. B's, I've got 4 of them. B, 4. C, I've got 8 of them. C to the A. And that is almost done. What am I forgetting here? What can I do? Well, I can simplify a couple things. I can simplify my constants. 36 divided by 9, that's 4 over 1. So I can just put 4. It's even easier. Now my B's, I have B's on the top and the bottom. I have 2 upstairs and 4 downstairs. So B's will cancel each other out, right? Like any of these letters will cancel out. If I have 2 upstairs and 4 downstairs, okay, I can cancel out 2 divided by 2, or B divided by B, B divided by B, leaves me with just 2 B's downstairs. So my A's are down there. My B's are only 2 downstairs. So I took care of that. Took care of that. Took care of my constants. And now I have 1 C upstairs and 8 of them downstairs. So I can only cancel out 1. And I'm left with 7 C's downstairs. So there's lots of steps of simplification to go through to do a problem like that. And when I ask you how to do this on the Google format, I say, how many C's were in the denominator of your problem, of your answer on number 12? Or how many, or what number was in the numerator of your answer? Because it's hard for me to format my questions in this fancy schmancy format. So I might ask you about the question and not what the exact answer is. So go through one at a time, look at your, move everybody around, and then simplify as much as you can. And then if you can cancel out those problems as well. Take your time, check it with a friend, call somebody up, don't be irrational, get to your point, don't last forever, and work on those together. Okay, in this section, functions, whatever you put in, okay, plug it in, get a result. So if we plug in certain numbers for X, then we're going to just do the work and get a result. And that's why plugging that into the function and getting a result out. So if I plug in -2, -2 times -2 is +4, and 4 plus 4 is 8. So that's my output. My input was -2, my output was 8. Plug in 5, -2 times 5 is -10, plus 4 is -6, okay? Plug in all those numbers, don't be thrown off by the fraction. -2 times -1/2. Okay, if you want to write that out, -2, put it over 1 times -1/2. Wow, look at that. Everything simplifies and cancels out. It's just +1, okay? But don't forget to add 4. So take your time when you're doing those problems to make sure you plug it in correctly. Answer the question, if you could live in any city, where would it be and why? Last but not least, we're going to graph some stories. You need to be able, actually not last but not least, sorry, psych. Use the bullet points below the graph to sketch a graph that represents the tortoise and the hare. So we did something like this in class, and the traditional tortoise and the hare, I will show you what that looks like. And so if I do the tortoise, he goes strong and slow and steady. He doesn't change his pace. His slope is going to be positive from the beginning of the race, where time is at 0, distance is at 0, and he's just going to go straight on up. And we know in the traditional story, he is going to win. Okay, so he gets to the end and wins. He doesn't stop. He doesn't do anything. If he stops, he's going to be flat. So it says they start the race together, 0 distance, 0 time. The tortoise goes slower, but he never stops. The hare is faster, but he stops 3 times. The tortoise just barely wins. Lights. Come on, lights. Get back on. I have a worksheet to do with my students right now. It still isn't turning out. Come on. Likes me to think I'm crazy. Okay, so the hare, he's faster, right? He starts at the same time. Someone put his dot right on top of the tortoise, and he's going to go faster, which means in less time, he's going to make the same distance. But then he's like, you know what? I'm doing so well. I'm winning. I'm going to just take a break. And time is going to tick tock by, but his distance doesn't change. And he's like, oh, the turtle passed me. The turtle passed him right here. Remember where our lines crisscross? That's where they're literally crisscrossing each other. So then he's going to go fast again, and he's going to pass the turtle. Okay, again, he's going to feel a little bit arrogant, and he's going to take another break. Tick tock, time ticking by, nothing will change. And then one more time, he goes fast. He takes a break, and then it's getting close to the end, and he is going to book it, and he's going to go so fast. But guess what? He is not going to get in the same amount of time. He's not going to get the same distance as the turtle. The turtle is going to be just ahead of him as far as the distance goes at the end of the race. So your graph should look something like that. Now, in the alternate universe, something different happens. The ninja, tortoise, and hare story, where they start the race together, okay? They stop and ninja fight, both of them, halfway through. So the turtle will go slow, the hare will go fast, but they're going to stop and fight. So they're not going to be changing their distance, because their distance is going to be chilling while they're fighting, doing their ninja fighting. Time is going to tick by, though, kind of like what you'll see right here, okay? The hare injures the tortoise, who doesn't change location the rest of the race. So think about what his distance is going to be if he's not changing his location. And then the ninja-loving hare wins because he's the only one who could finish, right? So that is going to be your graph on the right side. Let's see, those will be interesting to see. All right, last but not least, transformations with no visuals. So I know some of you guys rely on those graphs, those visuals, and you cannot always be able to do that. So if you had the point 1, 2 on a graph, tell me what that point would be after all these different transformations. If you reflected across the x-axis, what's that going to look like? So I know that this is my y-axis, this is my x-axis. If I go over 1, up 2, and I'm going to reflect across the x-axis, I am not changing my x. I'm not changing my left, right. I'm changing my up, down movement. So my y becomes the opposite sign. Okay, so over 1, up 2 is going to go down here somewhere. So it's over 1, down 2. Okay. Over 1, down 2. A rotation of 180 degrees, whether that's clockwise or counterclockwise, doesn't matter. We do something with our signs every single time. Dilation means you have to multiply each of your numbers by the scale factor. Sometimes we have to do that with fractions, and that throws everybody off, but that's not a fraction one. Translating it left and up means this left-right movement is always that x. The up-down movement is always your y. And then after reflection across the y-axis, so now we're at the same point, different direction. We are going across my y-axis now. So we went over 1, up 2. Now it's going to be over this direction. Okay, so we changed the sign of something different on that one. So take it a step at a time. If you want to sketch a graph, you can. Okay, but you need to not always have to rely on the graph. You need to be able to do it without a graph, without a visual, because you have to know those rules so well that they're expecting you to be able to do that without those visuals. And that, my friends, is all of Spiral Review number 7. I hope you have a lovely day.